Hello students, welcome to Heat 2, the Specific Heat Lab. This is part of the introductory lab for first year students. So first of all, when you talk about specific heat, you're going to be using this equipment called a calorimeter. So for a calorimeter, you consider this system as a thermodynamically closed system. So a closed system means the heat cannot escape from inside of the system. So whatever you do here, the heat that's being transferred in here is going to stay in the system. So mostly what you're going to be doing is you're going to be stirring this rod constantly and measure the temperature using the thermometer and probe it over time. So let's consider the following scenario. You start with the calorimeter with the water at the equilibrium. So this whole thing is going to be at room temperature. But once you drop the metal piece, a very hot metal piece inside of the system, what's going to happen is this hot metal piece is going to release the heat through heat transfer into the system, and this transfer is going to be through convection. Okay. So from fundamental physics, you know that the heat being released, the temperature, as the heat is being released, the temperature of the metal piece is going to cool down. So the temperature is going to be lower, and then you can use Q equals mc delta T, where m is the mass of the system, and C is the specific heat, and T minus Tf is basically the temperature difference. So specific heat is defined by the amount of heat per mass per temperature change. That's going to use to create the following temperature change. So right here, you will be measuring the temperature change because the system starts at higher temperature. And by system, I mean the metal piece, and the metal piece is going to release the energy, lowering the temperature of the metal piece down to the final temperature of Tf. Then again, as you do that, you would know that from the conservation of energy, since you don't know Q out, but what you can do is you use the conservation of energy. Since this is a closed system, the energy that's coming out from the metal piece is going to be stored in the water energy capacity and the calorimeter itself. So what you do is you're going to be measuring Q in. So whatever energy is being released here is going to be equal to the energy being absorbed. So instead of temperature reducing as in the first case, this one temperature is going to be increasing. So you change from the initial temperature of TW, which is the initial room temperature of the water, increase up to Tf. So you would be able to use this mc delta T equation to calculate the energy that's being received in the water side, and same thing here in the calorimeter side. So what you need to know is you need to know Tf, and then you can calculate C by equating these two equations. So since Q in and Q out has to be the same, you can put this equation equals the other side. And since we want to solve for the C, you can divide the whole equation by m times T minus Tf. So what you're going to have is you're going to have this equation is a little long, but you will know that C is equal to this equation, where C is the specific heat of this little metal piece. Again, in this part, since we're not gonna know the we can tell the specific heat capacity of the water by looking it up from the table, but what you won't know is the specific heat of the calorimeter. So instead of actually finding the specific heat of the calorimeter, we're gonna find the whole heat capacitance. So heat capacitance is defined by mass time specific heat. So I'm going to define a new variable called Ck. The big Ck is going to be the multiplication of these two terms. So by rearranging the common terms, you would get Ck in the place of Mk times Ck. Note that there's a difference between the small ck and the capitalized ck. Capitalized ck has a unit of calorie per Celsius, but the small c that we have all here is going to be in the unit of calorie per gram per Celsius. Okay, so this is what you call the heat capacity. This is what you call the specific heat capacity. So we're not finding the small ck here, but we need to figure out what is the big ck. Okay, once we know all of these variables, you can calculate C. And calculating C of the hot piece of metal is going to be what we're doing today. All right, so this lab is going to be divided into two parts since we need to figure out what is C, but before that we need to figure out what is CK, the big CK, the heat capacity of this calorimeter. So let's start from finding CK. How do you find CK? So part 1, you'll be determining the CK. CK is the heat capacity. Note, it is not the specific heat of the calorimeter. So first of all, you want to start with the calorimeter, but instead of having the hot piece of metal here, you're going to remove it from the system for now. So instead of having a hot piece of metal, you want to start by an empty calorimeter without any warm water inside. So by doing that, you measure the temperature as it changes over time, and then you pour hot water into it, and this hot water is going to change, right? So by doing that, the temperature would rise instantly. So what you can do is, you know that heat that leaves the water would actually go into the calorimeter. So heat that leaves the water is going to be the same as heat entering the calorimeter. You can use the same trick as previously mentioned to calculate that the heat capacity of the calorimeter is basically the temperature differences multiplied by mass of the water that's put in and heat capacity of the water. So from there you can tell what is CK. So now we need to figure out what is the final temperature and what is the initial temperature. So the way to do it is basically imagine the scenario. So you have this box of the calorimeter just sitting around by itself, and then you just sit down and wait. So right now the calorimeter is gonna start from the initial temperature of Tk prime. Okay, so this Tk prime is going to be your room temperature, and then you're going to pour in some water. So this water is going to be mixed carefully at 60 degrees Celsius. So 60 degrees Celsius is going to be your T prime W. And now once you mix them together, they would reach equilibrium of Tf prime. Okay, but then again, this is not ideal closed system, so there's going to be some heat dissipation. So what I'm about to tell you is what you're going to do. So you want to read the temperature of this calorimeter once every 1 minute. Okay, and be sure to read it down to the final decimal point of this thermometer. So as you do that, in the beginning, the temperature would be constant, and once you mix the water in, the temperature would sharply rise, and then it slowly decay afterwards. So this is from the heat loss outside of the system. Okay, so naturally your graph would be a flat line, and then it would instantly go up, and then it would go down once again. So by doing so, you need to figure out what is the effect from the heat leaking out. So to figure out this heat leaking out, the trick is you want to draw the line that cuts at the center of this little slope, and then create the area B and A such that the area covered by this geometric shape of A, the triangle A, and the triangle B has the same area. So whatever position where you could place this little line up here such that these two areas are the same, you can call that cutting point, the intersection, the final corrected temperature. So this final corrected temperature is going to be your Tf prime put in here. So once you know all of these T's and all of these M, be sure to weigh the water as well, and weigh the calorimeter. So from there you would know MW prime and CW, and this is look up from the table, and now you can calculate the CK. Okay, so this experiment is gonna last like 15-20 minutes, so be sure to plan around it, and you can go ahead once you got to the lab, go ahead and start doing this measurement first, because it's easy, and also you just read a constant number here until you pour in the water and see how fast it decays, and do this line correction stuff. Okay, once you're done with part 1, you can move on to part 2. So since you've already known CK, you can move on to the scenario I mentioned at the beginning. So you start with water inside of a calorimeter. Again, note that last time you used hot water. On this part, you're going to use some water at room temperature. So just put room temperature water in here, and then you before doing this, put a piece, the metal piece, into a boiling pot of water. So we'll have a separate pot to set this metal piece on a very high temperature. So once you do that, measure the temperature of the metal piece before it's being dropped into the system. Again, water at the beginning of this part is going to be a cold water, and then you drop this in. So again, so you know from the equation that we derived previously that in order to calculate C, you need to know what is CK, and this equation is missing CW. I'm sorry. I'll put it back in. Again, please refer to the equation on the first page. Once you know that, once you know CK, and you put a CW in here. CW is literally 1 calorie per gram per Celsius, so that was a typo. So sorry, but there's a small CW here. So once you look up the CW, you measure the mass of the water being put in here. You know CK from part 1. You can calculate the temperature difference, and once you weigh the weight of this guy, you know initial temperature, you know the final mixing temperature, then you can actually calculate the heat capacity of this metal piece. So by doing that, you do the same trick. So first of all, initially you would start from water at room temperature, and then you let it sit there until the temperature is completely dissipated. By doing so, once you start at the beginning, you start from water, just water sitting in the cup. So water sitting in a cup, it's going to stay at a constant temperature. And until you drop the metal piece at a minute mark of 5, this is going to start increase temperature sharply. So that sharp increase of the temperature is going to go up there, and then it's going to start slowing down as the time progresses. So by doing so, you could theoretically do the same thing. So you must correct the final mixing temperature by creating this vertical line along y-axis, so that you cut this graph in such a way that you form the triangle A and B that has equal area. So once triangle A and B covers the similar area, this slope here and this flat line here, wherever it intersect, you would have the corrected temperature. This corrected temperature here would be your TF, and once you know TF, you can calculate C. Okay, so this lab is pretty short and quite easy. So you do it twice. Again, I'm sorry guys, this equation is missing a small CW here, but you can feel free to refer back to my first slide where the derivation was done. All right, cool. So once you figure out CK, again, remember this capitalized CK is the heat capacity. The small c is the specific heat, so the units are different. There are different parameters, and as you go through this equation, you could actually calculate C and CK. So first part, calculate CK. Second part, calculate C. So in this lab, you will be turning in 2 of these plots, and be sure to use this correction. Okay. All right. Cool. Please enjoy the lab. Thank you.